Hi, y'all. So I'm going to go ahead and do an answer key for the quiz that was online. Your grade should be up, and this is similar to the material that will be on the exam tomorrow. So the first one is to draw the mechanism for this. So you can draw the CL leaving and then it attacking here or all in one. I'm not picky about that arrow. I just want you to know that this leaving behind a carbocation, and it makes AlCl4 minus. And this carbocation, actually, whenever you see a carbocation, a little flag should go off in your mind like, oh no, it's a carbocation. There's something that always happens with that, and you always have to check for rearrangement. And in this case, a hydrogen just shift from here to fill in over here so that you have a more stable carbocation that goes right here. So this is step one, generation of the electrophile and any rearrangement. Then step two is the benzene is going to attack right there on your carbocation. And when that happens, the benzene's aromaticity is actually broken. And it'll bond right here to this carbon. And then you have, so it's 1, 2, 3, 4. So you have carbon 1, 2, 3, and 4. Then at carbon 2, there's also a methyl group. This is just a dot of my pen. That's not a radical. There's still a hydrogen here and the carbocation forms. And you should note that there is resonance where this carbocation can move around the ring. But I actually did not count off points for that in this case. And then the AlCl4 can come in, or any base can come in, and the electrons from that hydrogen can restore aromaticity. That's step 4. And that should be your final answer. So that's step 1, generation of the electrophile. Step 2, benzene attacks. And step 3, aromaticity is restored. And so that's what I was looking for on this one. If you did not rearrange, you lost half a point here. And if I could tell you are trying to get there, I try to be generous with partial credit. For question 2, it asked, which one of these routes is better and why? And I saw some people focusing on the order in which they attach, like would it go meta or ortho? And that's actually not what we were getting at. Actually, they could attach in the proper arrangement either way. If this went first, it could be ortho, and then the nitro can be meta. In this case, the nitro could be meta, or it could be ortho or para, and the other one would still go to the meta position, if that makes sense. So the initial one could attach either here or here, and then the second one would attach at the other position. So the order of attachment in this case is not what's concerning to get ortho meta para. That's not what we're looking at. We're actually looking at the strength of the electron withdrawing group. So if you first undergo this reaction, this is a Friedel-Crafts acylation. So because toluene is ortho para directing, it'll either attach here or here. So let's just say it attaches here. If this attaches here, then we undergo step 2, the nitration. This is weakly deactivating, right? But with the methyl group, it's probably okay. And you'll get a substitution where we have the nitro down here. It's meta from the acyl group, and it's para from the methyl group, right? But on this second one, if the first thing you do is your nitration, this is significantly deactivated to the point where this reaction is probably not going to be able to do another substitution, so it won't react forward. So this is very similar. We had a practice problem in our recitation questions where we had 2 very similar to this, and the question stated that both of these would actually proceed in poor yields, and asked why they would both proceed in poor yields. And it's because they both start with an electron withdrawing group initially. But the next question was which one would be better of the 2, even though they're both poor. And the one that's better is always the one, as long as they get the substitution order right, the one that's better is always going to be the one that has the less electron withdrawing group attached first, as long as that doesn't affect the order of the substituents. In this case, the substituents could have gone either ortho or para. That wasn't the issue. It was all about the more electron withdrawing group coming on first. Okay, question 3. I'm really bad at drawing 7-numbered rings. It's embarrassing as an organic chemist. But the question was, is this 7-membered ring anti-aromatic, aromatic, or non-aromatic? And why? So the explanation was part of it. So if you just said it was aromatic, you got 2 points. If you gave a light explanation that actually wasn't super thorough, you got 3 points. And then if you gave a full, thorough explanation, you got 4 points. And so the full explanation requires that you know it's in conjugation all the way around, so p orbitals that are available all the way around the ring. And then that it has so an unbroken ring of p orbitals or unbroken ring of conjugation, and then it has 6 pi electrons or 4n plus 2 pi electrons, and in this case, that's where n equals 1. Either of those we would have taken. And then the very last thing is that it's planar. Or sp2 all the way around, I would have accepted that as well because sp2 are planar. So these were the things I was looking for in your explanation. And it's aromatic because it has the ring all the way around, because it has 6 pi electrons, and because it's planar. It's not 10 aniline, so it's planar. I did see someone say if this was a lone pair, it would have been anti-aromatic, or if this was a hydrogen and not a carbocation, it would have been non-aromatic. That does also show me that you understand. So whatever you can do to explain that and show me that you understand, that's what I'm looking for in those kinds of questions. Okay, and then question 3 was just what is the final product. So we start out with benzene, and if you have benzene with an acyl group or a carbonyl group with chlorine and AlCl3, that's going to be a substitution reaction, and it's going to be a Friedel-Crafts acylation. And then zinc and mercury, or it might have been zinc and copper with HCl under reflux, just gets rid of that right there. It's one of my favorite reactions because it just deletes the carbonyl group. I love it. Just makes it an R group. And then H2SO4 is actually a sulfonation. And because this is an ortho-para director, either this or this would have been the right answer. Usually you're only going to get one or the other. Usually it won't be like, here's both and tell me which one, unless it's asking about something sterically bulky, or if there's no other substituents around, there's 2 of these positions. So there's some questions like that, but for the most part, I don't think you'll be pitted against these 2 too much. But if there is a big sterically bulky group at the top, it will go to the para position just to have more space because of the electron repulsion here. So that's why we went with this as the answer choice. And then the very last question was, why are some groups ortho-para and some meta? And the answer I got for the most part was ortho-para are electron donating and meta is electron withdrawing. And while that's true, except for the case of the halogens, that's not actually the answer we're looking for. We're asking, why do they ortho-para or meta direct? And being activating doesn't tell us why it does that, but it is actually all about the formation of the carbocation. So if your electrophile goes here, your carbocation forms there. And I've drawn this before. I drew it extensively at the beginning of the chapter 15 practice problems that are on my YouTube page. That's just a methyl group. But there's a resonance structure that will show this carbocation goes all the way around the ring. And when it does, the positive charge ends up on the electron donating group if it goes to either the ortho or the para position. And that's good if it's electron donating. So we want the ortho or para if it's electron donating. But for the meta directing, you don't want a positive charge right there if that's electron withdrawing, because then 2 positive charges are right next to each other, and that's not great. That's like they're going to be fighting, kind of. So that was the type of explanation we're looking for, is discussion about the carbocation that forms on this rhenium ion, or when the benzene attacks and the benzene carbocation is formed, the position it's on in relation to the ortho-para or meta-directing is either stabilizing or destabilizing. So that is what I was looking for on the bonus question. So I hope that was helpful to y'all. If you have any questions, please feel free to reach out via email, and good luck studying.